So in this question we read, the density ρ of a sphere varies from its center to its surface according to this equation. So ρ equals ρ0 times 1 minus x over 2r, where x is the distance from its center, r is its radius, and ρ0 is the density at its center. What is the mass of the sphere? Immediately we might think to use m equals ρ v. So mass is density times volume. But we see the issue here is that the density is varying, i.e. it's not constant. And we can't just apply a density that's not constant times some volume. So how do we approach this? Well, if you think back to some of the other questions earlier in the paper, we might need to use calculus. But how do we go about thinking why we might need to use that? Well, the density keeps changing. So what we might want to do if we were going to estimate the mass is break the sphere down into sections where the density is roughly constant, multiply those by the volume in which they're roughly constant, and then add up all the bits of mass where we know they're relevant bits of information. So what do we mean by that? If I draw a sphere of radius r, and then I look at all the points that share the same density. So looking here, any point at the same distance x from the center will have the same density. So if we draw a very thin shell at a distance x from the center, and it's got a thickness of dx. So what we mean here is that all these points share the same density. So if we find the volume of this thin shell where they all have the same density, we could get the total mass in that thin shell. What we're really saying is that points within x to x plus dx approximately have the same density throughout that region. Again, the thinner we make that shell, the more accurate this representation is. So we just need to find out what's the volume of this very thin shell at distance x. And then we need to know the density in that region. Well, if we look at a shell like this, I'll just draw here to emphasize that it does have some thickness. The question has been helpful in giving us a hint that the surface area is 4 pi x squared. And then based on what I've been saying, we know that the thickness is dx. So how can we get the volume of that very thin shell? So I'll shade it in here to show what I'm referring to. Well, we know that the little volume in there will be the area, or cross-sectional area, times the thickness. Because we know from prisms or just general volume equations that if we have the cross-sectional area times thickness, we can get the volume. So you could imagine if we flattened this sphere out and drew something like this. We could get that the thickness is dx and the cross-sectional area is roughly 4 pi x squared. Now, you might appreciate that the area on the top surface and the area on the bottom surface, if we flatten this out, would be slightly different. But again, that's why this approximation becomes more exact the finer we make this. So the smaller we make dx, which is here, the more accurate it is to say that the top face and the bottom face have roughly the same area of 4 pi x squared. So we could get that the little volume, I'll just start using an infinitesimal here, dv, is 4 pi x squared, the cross-sectional area, times the thickness, dx. So how do we get the total mass in that small section? Well, we know the infinitesimal bit of mass in here will be the density at that radius, x, times the volume of that section, which we just derived is 4 pi x squared dx. So using the expression they've given, that would be ρ0 1 minus x over 2r times 4 pi x squared dx. So we found an expression for the amount of mass in a very thin shell of radius x. To get the total mass, we'll just need to sum up all these individual contributions. Summing up infinitesimals is just integrating. So if we sum these up, dm, we just get the sum between x is 0 at the center and x is r at the edge of the sphere of rho naught 1 minus x over 2r times 4 pi x squared dx. And this will give us our total mass, adding up each bit of mass in each section of the shell. Now this is just a simple integration from here on out. So I'll just take some factors. We have 4 pi rho naught. Then here, when we multiply it, we'll get x squared minus x cubed over 2r dx between 0 and r. Integrating this, we get 4 pi rho naught. This would be x cubed over 3 minus x to the power of 4. Then divided by 4, we get 8r between r and 0. Usually with these, when we substitute 0 into these polynomials, we'll get nothing. So we just need to substitute the r and get that term, which gives us 4 pi rho naught r cubed over 3 minus, well, we'd have r to the 4 divided by r, so we'll get an r cubed again, and then over 8. Simplifying this, we get 4 pi rho naught r cubed, and then we have 1 over 3 minus 1 over 8. Carrying on simplifying this expression, we would get 4 pi rho naught r cubed, then we have 8 minus 3 equals 5 over 8 times 3 equals 24. Now usually what a lot of students do is they'll multiply 4 by 5 and then simplify the expression, whereas for the NSAA and just general arithmetic, that is quite inefficient. So what I recommend is cancelling terms if you can. So I notice a 4 and a 24, which means I could cancel this down to a 1 over 6. Using this, we get 5 over 6 pi rho naught r cubed. So what some people might have done is do 4 times 5, which is 20, 20 over 24, and then they'd simplify it down to 5 over 6. So I've just skipped that step by simplifying directly from the 4 and the 24. So if you can look for any cancellations, it's best to avoid multiplying in the NSA just because time is so limited. And if your arithmetic isn't quite up to scratch, it's usually easier to do some divisions than longer multiplications and then simplify it down. So I do recommend this method. So this is the total mass. 5 over 6 pi rho naught r cubed. So if you check the section, this is B. So the answer is B. 5 over 6 pi rho naught r cubed. Now I just want to have a think about this answer. So this isn't needed for the question, but it's good to build some intuition as to what's happening here. The little bit of mass that we had in each shell was rho naught 1 minus x over 2r times 4 pi x squared dx. A question that we typically ask in physics is about averages or mean. So what would be the average density in this setup? Well, if you look at this, the density is decreasing linearly. So if I drew rho against x, it would be going like this. But the infinitely small volume, dV, is increasing quadratically. So our density is decreasing, but our volume is increasing by a factor of x squared. And so as we get further and further away from the centre, we'd probably expect more of the mass to be concentrated further and further out, because even though the density is decreasing, the factor by which the volume is increasing is so much more. So if I were to guess where the average density would be, I'd expect it to be at some radius closer to the edge of the circle. So I'd expect it to be, if this was halfway, like r over 2, I'd expect it to be somewhere between r over 2 and r. Now, let's check if this assumption is right. Well, we got that the total mass is 5 over 6 pi rho naught r cubed. And if we wanted to find the average density, well, what is an average? An average is telling us that if we had the same thing every time, we'd get the same result. So if we just divided this mass, this total mass, by the overall volume, we'd get the average density. Because if we just had this average density times the volume of a sphere, we'd get the same mass compared to this setup, where the volume is varying in a strange way. The density is varying in a strange way. So if we just do the mass divided by the total volume, we would get the average density. Now this is 5 over 6 pi rho naught r cubed over the average, over the volume, which is 4 over 3 pi r cubed. Just to reinforce what we'd actually done earlier, if you notice, the total volume of a sphere is summing up all these infinitesimal shells, 4 pi x squared dx between 0 and r. And if you carry out that integration, you might find that you do actually get the volume of a sphere, 4 over 3 pi r cubed. You might want to challenge yourself to prove this with a circle, where the thickness is dr and the circumference is 2 pi r. So if you wanted to get the total area of a circle, we would add up the area of each of these sections, which would have length 2 pi r, thickness dr, this would be the little area of that strip, and then integrating that between 0 and capital R, you would get pi r squared, the area of a circle. So going back to this, we get 5 over 6 pi rho naught r cubed over 4 over 3 pi r cubed, where we can cancel the r cubed and the pi, and 5 over 6 over 4 thirds would be 5 times the 3 over 4 times the 6 times rho naught. You can cancel 3 and the 6 to make a half, and we get the average density is 5/8 of rho naught. So let's check at what x position this is. So if we set rho naught 1 minus x over 2r, the formula for the density at some position x, equal to 5 over 8 rho naught, we can see here that 1 minus x over 2r equals 5 over 8. So x over 2r equals 3 over 8. So x would equal 3 times 2 over 8 times r, which is 3/4. So 2 over 8 is a quarter times r. So this average density is roughly halfway in between r over 2 and r. So it's at 3/4 r, 3r over 4. So as expected, because most of the weighting of the volume or the density is in the regions further away from the center, the average density would be found somewhere closer to the edge of this sphere. So we get x is 3 over 4 r. Now, another way that we can see averages or means that might be useful for when you're approaching physics problems is in a sample x, if you multiply it by the probability of achieving that value of x and sum up over all the values of x in the sample, you get the average value of x. So we'd call that x with these angled brackets, or you might call it mu. Now, the equivalent here, if we wanted to find the average density, well, we have the integral of the density of x. And then the equivalent of the probability here would be the small volume at which we have that density over the total volume. So if you wanted to find out the average density, you would do, well, what's the density at that position x? And then what fraction of the total volume does that take? That would be playing the role of the probability here. And then rho x is the sample values that we'd be taking. And integrate this over the whole volume, which means from the radius x is 0 to the radius x is r. This is the equivalent of saying rho of x times the infinitesimal probability of finding mass at that section of x. This would give us our average density, or rho average as I called it earlier. This is quite a useful concept in physics to appreciate, just because a lot of time we could deal with averages rather than trying to break things down into small bits. So it's easier to work with a composite body, working some average property of it, and then using this for some calculations. Although a lot of the times this will need some integration. But when things vary linearly, you can usually use something such as halfway points, or kind of guess or intuit where the average might be, depending on the relative weighting of one factor compared to another. So just to hammer down this point, if it was rho of x times 4 pi x cubed, which I'm making up, this would have an even greater dependence on x, or the radius. So even larger volumes further away would take even more of a weighting. And so the average value, here for rho would probably be at some x position x greater than 3r over 4. And then if we had x to the 4, x to the 5, and so on, we'd expect the average density to be found at some x position getting closer and closer to the edge as the weighting gets more and more important depending on the x value that you're at. So this was just a tangent to the problem, but it's good to think about why did they ask this question, which is just to find the total mass of the sphere, but it's quite useful to find the average density. Hopefully that all made sense, but if you have any questions, please write them in the comments and I'll be sure to respond.